All right, welcome to the DDPS seminar, everyone. It is an honor to host Anima, Anandkumar, who is a brand professor at Caltech and director of ML research at NVIDIA. She was previously a principal scientist at Amazon Web Services. Anima is really a pioneer of the neural operators, and today she is going to talk about ML for solving PDEs, neural operators on the function spaces. So Anima,
Thank
it's
you.
all yours.
Thank you, Young-Soo, and great to be here. Sorry for the delay. The WebEx I haven't used in a long time, so and
No
I
worries.
had some teething problems. But so I'm happy to talk about neural operators and what is the methodology behind it, why that is suitable for different scientific applications, including solving partial differential equations, and also why not just the standard neural network tools, right? What is special about neural operators? Yeah, so indeed, if you want to think about modeling multi-scale processes in a variety of scientific domains, this is very challenging, right? I mean, the scales are enormous. You can go all the way down to problems at the quantum level, looking at interactions as wave functions between electrons in a molecule and using that to predict the properties, especially when it comes to designing new drugs or materials. This is important. All the way to the planetary scale, if you want to predict the weather or climate, how we can look at microscopic interactions and the impact it has globally at planetary scales. And that's the aspect that is so challenging to model. And of course, there's so many other problems in between as well that are multi-scale in nature. And this is different from text or image processing, right? That you've seen a lot of exciting developments, but that doesn't directly translate into our ability to model these processes. Text is discrete data. Again, image processing, typically you just think of doing that at one fixed resolution, right? And it's object-centric. In natural images, our main goal is to reduce from this pixel space to some low dimensional representation that is centered around objects. For instance, segmenting the objects, being able to recognize the objects. So that's where a lot of the focus is on, right? Going from these pixel dimensions to lower dimensional space. On the other hand, if you think about these multi-scale processes, there's information in all scales, right? So you cannot very easily reduce it to some high-level representation like we do with image processing. And so we need to think of different frameworks to be able to nicely capture all of the scales and do high-fidelity modeling. And as an example, I want to show the challenges in modeling climate. The one big source of uncertainty, in fact, the biggest source of uncertainty is the presence of these low-lying clouds, what we call stratocumulus clouds, and the turbulence in them. So the ability to model the turbulence at very fine spatial and temporal scales is important in order to get the right answers, or these micro scales ultimately impact the macro behavior. And what my colleague Tapio Schneider estimates is you really need to go down to 1 meter spatial resolution planet-wide. And that requires about 100 billion times more computing than what we have today. And so if we are trying to do standard numerical methods and we need to go to these fine scales, it's just very out of reach to be able to do that, right, in a brute force manner. And so right now, our capabilities are barely getting to 1 kilometer, right? So that's also not fully there. We are, still getting to that resolution. And so there's a big gap between what we can do today versus what we really need to do to capture the fine scales in climate modeling. And so that's just one of the examples. The same is true with quantum chemistry or multitude of other examples I showed you, we cannot get to the level of computation needed to capture all the scales of the problem. And also, in this case, we are going from bottom up physics, right? So we are starting with partial differential equations. Each time we are redoing all of the computations to get us to the answers. So the question is, what is the role of data-driven methods that could learn from previous data and be able to do these computations much faster? So this is where I think machine learning can have a very big impact, helping us build on top of accelerated computing. GPUs are indeed the workhorse of AI. So getting all those hardware accelerations and efficiency, and of course, supercomputing scale. So we'll use all of that, but machine learning is really the enabler of that scale, right? It's going to help us leapfrog and get us very big speed ups in terms of being able to do much faster computations. If we can avoid the fine grid required for numerical methods and get away with coarser grids, get away with not having to do intermediate iterations and get to the answers faster because we learn the features that are relevant to that domain, then we can really leapfrog in our computational abilities. And I think that's the promise. And we'll also see in many applications, we are able to get very impressive speed ups, and we're able to maintain the fidelity or sometimes even surpass it compared to traditional methods. Yeah, so let me first start with the framework and give an overview of what neural operator is, right? So what makes it different from standard neural networks? I think I told you just a few slides ago that we cannot use the same models as text or image processing because we need to capture all of the scales. And I think that's the key difference. If we used any of the standard neural networks for image processing, whether it's convolutional neural network or vision transformers, they're typically trained to work at a fixed resolution. So you have training data at one resolution, and you also have testing data at the same resolution. On the other hand, if we are thinking about solving scientific problems, as I mentioned, we need to capture many different scales. And not only that, we need to be able to query at any scale, right? So if you use any of the scientific methods, any numerical methods, we have the flexibility of having different grids, right? So in fact, different problems entail different shapes of grids. For instance, the airfoil, typically we have this non-uniform grid because you want more finer grid near these sharp points. And so this flexibility to go different shapes of grids as well as query at any point, because the phenomenon is in a continuous domain, is important. And so standard neural networks don't have that capability. And so the question is, how do we design neural operators that can mimic the capabilities of current numerical methods, but are also having high fidelity, are expressive, they're able to capture the multi-scale phenomena, and they're fast, right? So we need to be able to do all of this at once. So that's where our inspiration comes from, the ability to solve first linear partial differential equations. So as a thought process, if we start with asking what is an efficient way to learn solutions for linear partial differential equations, you can think of this form of the solution, right? The inverse of differential operator is the integral operator, and we can look towards building a block here that learns to solve this integral linear operator. So this is now a building block that can solve linear partial differential equations. For instance, the heat diffusion equation is a linear partial differential equation. And in some cases, we even know this kernel or this Green's function analytically. In other cases, you have to numerically compute it. But the key is here solving linear partial differential equations involves learning the kernel or this Green's function and also being able to integrate that on the continuous domain. So because this integration is over the continuous domain, you can now give your input at any different discretization, right? And you would still be able to have the output be at any discretization. So that's the key difference from a standard neural network where the input is only in a fixed discretization, a fixed grid. Here we have the flexibility to have the input in any point in the continuous domain because it's computing this integration at any point. And so that's the key aspect that is, will be different from standard neural networks. And also now the question is, how do we compute this efficiently, right? So there is two aspects. One is how do we compute this efficiently? The other aspect is how do I extend this beyond linear equations to nonlinear equations? So many phenomena of interest that I showed you, fluid dynamics for climate modeling or quantum chemistry, right? So, many of especially the approximations of that become nonlinear problems. So we need to be able to handle nonlinearity. And so that's where we introduce a more general framework that takes these blocks that learn integral linear operators and compose that with nonlinearity. So these compositions of integral linear operators with nonlinear activations, they can be standard nonlinear activations like ReLU or GeLU, usually GeLU because we want also second order derivatives, right? In many of these differential equations, they involve second order derivatives. So we want that smoothness, and so we use a function like GeLU for a nonlinear activation. But that's a detail, but the general framework is that by composing linear blocks with nonlinear activations, we get an expressive model. And this is the same philosophy as a standard neural network, because even there, you have a linear function and you compose with nonlinear activation. The linear function in fully connected neural network is matrix multiplication. In convolutional neural network is convolution, right? But the same philosophy holds here, that we compute a linear operator and then we compose with nonlinearity. The only difference is this is now learning a linear operator as opposed to a linear function. So this operator maps a continuous input to an input in a continuous domain to output, which is also a function on continuous domain, right? So that's the main difference.
Anima, Madi has a question
Sure.
about, are the inputs here location, time, and the outputs the solution of the equations?
So the input can be both space and time, right? So to me, input is any function on a continuous domain. And that domain could be space or time or both or anything else as well. So this general framework, yes, that's one option.
Okay, thank you.
Great. And again, yeah, if there are further questions, yeah, do feel free to interrupt me.
Sounds good.
So that's the framework. Now, of course, one thing I haven't told you is how to learn these integral linear operators efficiently. And so one framework that has been very successful is what we call Fourier neural operator, where we relax the kernel to a convolutional kernel. So meaning you only look at translations, right? And this is indeed a limitation compared to the general kernel. But because we compose it with nonlinear activations, we can show that it's still expressive. And in fact, both this original neural operator as well as the convolution-based neural operator are both universal approximators. So you can approximate any nonlinear operator, which is a mapping from one function space to another, with these frameworks. And I think this is important to be able to capture, as I said, any nonlinear operator. So, but of course, this, I have just made this simplification, but what is this bias, right? Why is this more efficient to learn a convolutional operator? So this is where we can do change of basis. We can go from convolution to element-wise multiplication in the Fourier domain, for instance. So we know Fourier basis is a good inductive bias for many problems, including fluid dynamics. It's been used for numerical methods as well. So we can use that inspiration and say Fourier domain is a good inductive bias. And not only that, it becomes much more efficient to learn the coefficients in the Fourier domain, right? So this way, the integration over the continuous domain just becomes matrix multiplication. So this is efficient, and we can learn the coefficients in an efficient manner. So that's the principle. It's very simple, that we can transform our input into the Fourier domain. We learn the coefficients in the Fourier domain, and we go back to the standard domain. And then we do nonlinearity in the standard domain, which could be space and time, and we then repeat this again. So a few points here, right? So first of all, if we did just this convolutional operator in the Fourier domain without nonlinearity, that would be limiting, right? So, and in fact, that's what the numerical methods do. They transform to the Fourier domain, and they just do iteration there. On the other hand, we have nonlinear activation. So we have the now flexibility to not just, it's not just limited to the Fourier spectrum of the original signal. We're also learning features over nonlinear activations. So that's a benefit. The other benefit we can get is through regularization. We can capture only the low frequency modes in the first layer. So we just filter out and only retain low frequency modes here. Of course, if you didn't have nonlinearity, this would be a strong aliasing, right? So this would lead to errors because many signals of interest have high frequency components, so you can't just threshold them. But on the other hand, because we have nonlinear activations present, we can further transform the signal and still have the ability to capture high frequency content. And that's why we are able to provide the guarantees of universal approximation. Even though in each layer we are using a regularization to keep low frequency modes. Of course, that's a hyperparameter of how much do you threshold to retain low frequency modes versus how many layers do you have, right? So both are hyperparameters we can choose for different problems, but really the benefit is the ability to now make learning efficient as well as keep the discretization invariance, meaning I can now input my signal at any resolution, or with any resolution, I can still capture the signal through Fourier transform, right? Because I can do Fourier transform at any resolution. And that's a key ingredient that makes this overall framework end-to-end discretization invariant. By that, what I mean is, let me first show you just an example, a proof of concept in terms of showing how we can, train in one resolution and test in a different resolution, right? Which wouldn't be possible with standard neural networks. So we're training using only coarse resolution data for this Navier-Stokes equation. And we do that over different initial conditions. And then at testing time, we provide higher resolution inputs. And then we look at how well does it predict, right? And what we see is, indeed, that does predict pretty well. And can see that, in fact, in the frequency spectrum as well, that the prediction is very graceful, even beyond the scene resolution, meaning it extrapolates to higher resolution without seeing it during training. So this is what we mean by zero-shot super resolution. And you can see that here, that there is right? I mean, these systems are dissipative, so you do see the drop off of the energy spectrum. But when we are giving training data at a fixed resolution, we only see these wave numbers, right? So we have no idea what the higher wave numbers are. But in cases where there is a nice drop off, our framework is able to track that compared to other standard frameworks like UNIT. I think there was another question.
Yes, there was another question by Madi. He said this also assumes that the set of equations that represents the physics in one scale is also valid in another scale, right?
Yeah, we are currently assuming there's only a fixed set of equations, right? So in a way, I mean, I haven't even used the equations, right? So if you're using the equations in a physics-informed manner, that would matter. In this case, we are just giving data, right? There's no physics knowledge built into the model. But what really, where this will work well is when there's a nice drop off in terms of energy, right, in these higher frequencies. If you, for instance, have something very arbitrary like this, right, some arbitrary spectrum here that is having very high energy content, we cannot expect to capture it because we have absolutely no information about that.
All right. He also asked, what is the difference between two scales? Factor of 10, factor of 100?
You can see that here, right? The wave numbers. So these are the wave numbers we provide. We can go all the way up to 100. So we provide a little more than what it's 25 wave numbers or 30, something like that. And we can go much further.
Sounds
So
good.
we can go to any scale, right? The prediction can happen at any scale.
Sounds good. Thank you, Anima.
Yeah. Yeah, so just to kind of make this point about discretization invariance, what can we guarantee, right? As I mentioned, we cannot guarantee that we will give you as error-free answer at any resolution because that's impossible. If we do not see higher resolution inputs, there's no way we can capture all of the information about it. On the other hand, what we can guarantee is graceful degradation, right? Like kind of having consistent answers even as we refine the mesh. So the idea is you keep refining the mesh and asking what is the value at any point here. You should converge to a limit, and ideally that limit should be closer to the ground truth operator, right? So what we are guaranteeing is this kind of convergence. And this is something you may not otherwise see in other frameworks. And so just to kind of make that point clear, standard neural networks do not have this ability because most of them you can't even query at any resolution, right? So the standard architectures expect always the resolution to be fixed, whereas neural operators remove that dependence. There's, of course, an intermediate step where you could use interpolation on top of standard neural network. So you train your neural network at a fixed resolution, you use a standard fixed interpolation, whether it's bilinear interpolation or any such framework you can use on top where there's no learning for interpolation. So that framework indeed allows you to query anywhere in the domain, but it does not guarantee universal approximation because the neural network just learns at a fixed scale, right? So it is not learning in the function space like we do with neural operators. And that to me is the big benefit we obtain here. Yeah, so just to reiterate, the framework of neural operators is taking ways to compute these integral linear operator and composing with nonlinearity to give it both expressivity, but by learning blocks that compute integral linear operators, we still keep discretization invariance. And so that kind of like, ability to have both aspects of discretization invariance and nonlinearity is crucial. So there's an extensive library. I encourage you to go check it out. I know it's open source. Also contribute to it. Would be great to hear your thoughts. Where we do have implementations of the Fourier neural operator that I mentioned, but also there are other approaches, right, in order to be able to estimate this, for instance, through graph-based method, because you can learn through a graph neural network and message passing, what is the relationship between nearby points? And then you can turn it into an operator, because once you learn the kernel, you can approximate the integration as summation. So this works well if the phenomena is fairly local. So it's much harder to do for global dependence, like in fluid dynamics, because you would need the neighborhood to be very large, and that is expensive. So I think there are frameworks where the graph-based methods are effective, and then the other domains, especially with where we know the operator is highly non-local, where Fourier-based methods are effective, because we can express these kind of global dependence efficiently through Fourier transforms. Yeah, so far what I mentioned was just computing on a, practical implementation was computing on a uniform grid, right? Because Fourier transform, the efficient implementation is fast Fourier transform that assumes uniform grid. And if you try to do Fourier transform on non-uniform grids, sure, there are algorithms, but those implementations are not efficient. And so we wanted to keep the Fourier transform as fast Fourier transform on uniform grid. And the way we decided to handle non-uniform input domains, right? The physical space, for instance, this airfoil wing, this is a irregular geometry shape. And we also want our grid to be irregular to capture that non-uniformity. So this is our input domain. So what we propose is to learn a deformation from this to a uniform grid in a latent space. And we know from topology that such deformations exist. So if you assume this is homeomorphic to a torus, you can learn that transformation, right? And if not, you can also you decompose the domain into multiple parts and piece them together, which is a detail from topology. But the idea is this is very general. So in general, you should be able to learn the transformations from a physical space that is irregular to a latent space that is regular. And so what we do is we learn such deformations point-wise. And this way we can go to a latent space and do efficient computations and come back to the standard domain. And so you can see that where we predict deformation for plastic forging here. And again, we see really impressive speedups, about 100,000 times speedup over standard numerical methods. And you can see that geometry is changing over time, and it's able to maintain and do that prediction. So this is another example where we, can handle irregular shape in the sense that the fluid is now flowing through a catheter with all these triangular shapes, right? So we propose triangular shapes as a way to limit the bacterial contamination. So what's known is the bacteria swim upstream to the fluid flow, and if we can reduce the bacteria by trapping it in these triangular places, then we can reduce the contamination. And so one benefit with these methods is that we can do inverse design very effectively. So not just inverse design, any kind of inverse problems, because the trained neural operators are differentiable, right? So we can directly get the gradients back. And so what we did was to ask, how can I find the optimal triangular shape to minimize the bacterial contamination? So here the contamination should be ideally zero, because we don't want the bacteria going back into the patient. And so we were able to do that by doing gradient descent, which is very fast and effective. And that's how we were able to very quickly propose a design, and our collaborators 3D printed it and tested it in the lab. And this is just a visualization of how you can see many particles are getting trapped in these triangular grooves. Yeah, and so this is another here demonstration with airfoil. If you want to optimize for lift versus drag, right, we can directly do gradient descent and come up with this. And here we are having the simulation of the fluid dynamics around the aircraft wing, right? So we are only training for the forward model. So in the forward model, we have many different aircraft wings. We are predicting how, what is the fluid dynamics around that. And then we can directly do the inverse problem. So the key is you don't need to know what is the optimal design when you're doing the training of the neural operator. And you can do the inverse and come up with the optimal design. Yeah, so far I did not incorporate any of the physics. I think there was a question earlier asked, right? So, how does it capture the different scales? So, in terms of if you want to really capture the fine scales, and we need to do that with high accuracy, we would need to know the equations as well. And so the idea is if the data is only at coarse resolution, I now have the flexibility to express my equations at a much finer resolution. And so this way we can capture both data and the equations, and we can get to high fidelity results. And so we can then do zero-shot super resolution very well, even at higher resolutions. And we can also further fine-tune our model because, during training, we have a variety of initial conditions and solutions. But at test time, we have a single initial condition, right? So we want to do well on this. We can further fine-tune with the equation laws on this specific instance, and that way we get to a better error. And so we can also do better transfer learning with physics-based losses because we can, learn the operator, say, on one Reynolds number. If you want to fine tune on a different Reynolds number, there is a distributional shift. But having the equation laws allows us to quickly figure out what the distribution changed, right? What parameter changed, and still utilize the information that was, in the earlier trained model. And so this leads to faster convergence. So far what I told you was to learn deterministic maps between function spaces, right? What about learning probability distributions on function spaces? And indeed, this directly, asks similar questions as we've seen with generative AI, whether it's text generation, image generation, right? So they're all learning probability distributions. Can we do the same? And indeed, for scientific computing, that's very important, right? So inverse problems, if you want the posterior of your inverse problem, that's a probability distribution naturally, right? Uncertainty quantification, learning like chaotic dynamics. So you want to ask what are the different attractors and what is their distribution. So all of this are problems that require a probability distribution. And of course, if you're looking at stochastic differential equations or other stochastic processes, those are also, involve learning probability on function spaces. So what we've recently derived is a diffusion model, but now on function spaces. And so we are doing that by extending what is known as score function in diffusion models in finite dimensional spaces to now score operator, right? So this operator maps a function space of one domain to another. And in this case, what we want to do is map, instead of Gaussian noise, a Gaussian random field to the output distribution. And so this is the key difference here. With Gaussian random field, you can now sample at any resolution. So you're no longer limited to sampling at the resolution of the training data like we see in image generation models. And that's how we can now, do this training at low resolution and generate high resolution images and still get, very good fidelity of what we generate, right? So if you now have a density of initial conditions, you want to capture that random distribution of solutions for these given initial conditions. In this example, you can see that we can do very well. So I wanted to see if there are further questions before I maybe showcase one or two examples of using these various methods.
Yeah, Madi, do you want to unmute yourself? I see you raise your hand. Madi, are you there? I don't hear him. Okay, so any other questions from audience? Anima, you can move on.
I think
you can move on, Anima.
there's another question.
No, yeah, I don't think so. You can move on.
Okay. Yeah, so to give you some examples, we trained using these Fourier neural operator and its variants on weather data. So this is era 5 reanalysis data that's available since the 1970s. So having this wealth of historical weather data allows us to train a model that's very accurate as well as fast. So here's a visualization of the atmospheric rivers, and you can see that it can capture these very wide, those are thousands of miles wide phenomena that has a huge impact on whether there are storms or drought in the western coast here. And not only that, it's very fast. It's about 45,000 times faster than current numerical weather models. So you can also see that with trajectory prediction, we can predict these wind conditions, and the high wind conditions are in purple, and you can see our prediction closely follows the trajectory of Hurricane Matthew, which was certainly not in the training data, right? So we are looking at how well it does on new hurricanes, and it's able to give you a good uncertainty bound around the trajectory of the hurricane. So these are some more details, and we also have some of our models open source there. I welcome you to go check it out. And what you can see is the ability to have big speedups over current numerical weather models, and at the same time, good accuracy. So what would take hours on a CPU cluster for current numerical weather models takes less than a second on a single desktop GPU. Yeah, and we continue to improve this. I think we just recently talked, I think yesterday the talk was at iClear workshop on climate AI, where by incorporating the spherical geometry, so instead of the fast Fourier transform on Euclidean space, we now have spherical harmonics, and we build that into our model. And that leads to even better extrapolation. So you can do much longer rollouts than what we had trained for. We trained it just for a few time steps of 6 hours or so, right? So we have very short range training, but we can extrapolate the model to long rollouts, and there's good stability. And we continue to improve the forecasting skills as well compared to the IFS, which is the current numerical weather models. So we've also used in a number of other scenarios to mitigate climate change. Carbon capture and storage is a big aspect. So how do we model the buildup of pressure as carbon dioxide is pumped into these wells? So we are now able to do multi-well modeling. So being able to look at multiple wells at once, and if you have a permeability map, so you know how permeable the ground is, and we can then use that as the input. Given a permeability map, we have high resolution, a fine grid prediction within the wells, as well as a coarser grid to connect the different wells. And you can see that we can model the gas plume evolution as well as the pressure buildup. And we can do that over 30-year range, and we can even do further if needed. But the key is you can see that it has a very big speed up, about 700,000 times faster than current numerical weather models. So these are applicable in many other scenarios as well. Predicting air turbulence for drone flights or other flights is important. So we've been testing it in the lab by looking at turbulent conditions here and using laser measurements and showing that we can do very nice real-time fluid prediction directly from noisy experimental data. And so we continue to test models like this also in the physical hardware on the lab to see how well we can stabilize the airfoil wing and many other cases. So just to show, like at Caltech, we also have the fan array where we can test this very carefully on different kinds of wind conditions. So I think I already mentioned the catheter before, so yeah, so, again, sorry for the delay, but I hope you got a good overview of what neural operators are, what is the principle behind designing them, and how they differ from standard neural networks and their ability to capture multiple scales and do inferences in a discretization invariant manner. Thank you.
Sounds good. Thank you so much for the wonderful talk, Anima. I guess, did I miss the question from the Joseph? Let's have a Q&A session, by the way. Joseph asked, are there any special considerations for using neural operators on inverse problems?
So there are different options, right? So you can learn the neural operator for the forward problem and then just take gradients, differentiate through the model, or you can directly learn the inverse mapping. And so there are both options, or you can couple both of them as well. And also in both of these cases, you can ask, how do I also incorporate the physics, right? So you can also do the physics informed version. And then there is the aspect that to capture the not just point estimates, but to get the right posterior distribution, can we use diffusion models? So what I propose diffusion models on function spaces.
Thank you. Okay, another question by Huwei. For the CCS case, have your team try to explore the super resolution property of FNO?
Yeah, we can certainly give predictions, but we don't have the ground truth, right? So we are now working with some partners, getting real data and validating on that.
Awesome. Okay, next question is by Fei Zhao. What do you need to train the neural operator? Do you need the original PDE? Can you learn on noisy ground truth?
Yeah, so we don't need the original PDE, right? So the framework I described is very general. The input can be any function on a domain and the output is a function, right? So you're learning that mapping. And so you can take data from solvers, existing solvers, like I showed you the Navier-Stokes example, or you can take the weather example where the data is already there, the historical weather data, the reanalysis data, and we train on it. So it can be very general.
Sounds good.
And
Okay.
if the equations are there, we can incorporate that as a loss function in addition to data.
As you show in Pinot, right? Okay, the next question is by Rui Pang, and he asked, for the function mapping to learn from PDE coefficient to solution, any ideas what function spaces it is in, and is the mapping unique?
So to learn from the coefficients to the solutions, if the PDE is well posed, you assume there's a unique solution, right? But we don't need to even assume that. As long as we have the data that learns the mapping, we can do that. But of course, if it's unique, then you have a good error and you can learn this well.
All right, sounds good. So I don't think there's any other question, but
I have a question. Raise the hand.
sorry,
yeah.
I think
So for the FNO, can you say more about like the boundary conditions, especially like non-periodical boundary conditions, and also for the in the carbon storage case, you showed that have like the coarse grade far fields and also like near the well, like have the high resolution grade. So how you make the boundary conditions consistent between these two?
Yeah, those are great points. So for the first, generally like for non-periodic cases, right? The Fourier branch may not capture that very easily. I mean, you can correct that with Fourier continuation methods, and we also propose that. But we also have alternative branch, so we have skip connections, and so that's a very efficient way to capture non-periodic conditions, and so we have architectures that handle that very efficiently. So in terms of like for the specific case of CCS, what we did was a nested FNO model. So we now have different FNO models for within the well versus outside. We have multiple levels, and yeah, so they just share the information across them. That
Alright.
makes sense.
Sounds good. I
Thanks.
think, do you have more question? No? Okay.
No.
So FNO is known to require many data. So, and from your experience, PNO, if you incorporate the physics, then do you see that you require the less data is required?
Absolutely. Our data requirement goes down significantly. And of course, it depends on the hardness of the problem, right? So, some cases you may even do with one data point, that's the physics-informed neural network setting, right? So if the optimization landscape is very efficient, you don't need any data at all. You can directly solve for the equation laws. And then there are others that are high dimensional and very hard, and you may need more data. So there's a whole spectrum of problems.
Okay, sounds good. I have a just clarification question. So you said that DeepNet is not discretization independent. I thought it was discretized.
So there's the original DeepNet that was proposed was on assuming a fixed input grid. So the input grid was assumed to be fixed. The output is still a function. So the output can work at any resolution, but the input was a fixed grid. And then later on, we proposed a solution, others proposed a solution as well to fix that. But anyway, I wanted the original one had that issue.
Okay,
but right.
yeah, I just wanted to clarify because I think the current version of the DeepNet
that doesn't
is
happen.
independent of the, okay. Another question from CO1 Chang. What is the regularity assumptions needed in the function spaces if the solution is of low regularity? For example, the domain is singular and the functional is rough. Can the current framework be applied?
Yeah. So we are working on like kind of extensions of this in terms of practical architecture, but there's already theory showing that you can use Fourier neural operator to approximate those well as well. Like Sam Lanther and Andrew Stewart have like a recent paper. But yeah, this is something we're working on.
I see. Okay.
Yeah, I have another question for the
Alright, go
transfer
ahead.
learning one. Yeah, so for the transfer learning, if the differential equations are different, like for different problems, do you think that transfer learning is still helpful or not? I know like in the same equations, probably it's like helpful from, but from the point of view of different differential equations.
Yeah, that's great. And that's unclear, right? It's again the same as any, what we see in other vision domains, like how much is the shared features. You may think some of it is still shared because numerical methods, right, like kind of have similar approaches for all of these domains. So it may still transfer, but yeah, it's a good question, how effective it is. We haven't tried it so far.
Yeah, some comments on that, Chinkai. I mean, transfer learning, not on the neural operator, but on the traditional neural network sensing sense. It has been applied, the pre-trained model for the different PDE, and use that to accelerate another neural net model for another PDE. That has been demonstrated, but I guess it's an example by example.
Yeah, exactly. Yeah, but I think I expect that there should still be an advantage. You're right.
Some are useful, right? All right. Any other questions from audiences? Oh, yes, we do. Okay. As the question from Pratanu, when you compare the speed up, do you consider the training or data generation time?
So, no, and in these numbers, we don't. First of all, it's still not a significant amount, right? So, because to me, data is just something that, you only do training once, right? And then inference is running cost. And so this is the standard way we would evaluate any method. So, because also there is cost that goes into programming these algorithms, even for traditional methods. So, so I would just, to me, that's something that, happens before the solver comes online. But we do report that in our papers.
Got it. Another question by Madi. Can the method extrapolate to new and unseen geometries?
Yeah, in the geometric FNO that I proposed, yeah, it does. That's how you can see that even online changing geometry of the deformation, it's able to track.
But you should have some mapping from, one geometry to another. That
No,
mapping
we just
must be
learned
available.
that. We learned that
Yeah,
mapping.
okay, yeah. All
So
right.
it can handle different geometries. That's how we're able to generalize it.
All right, sounds good. Is there any other questions from audience? If not, let's thank our speaker Anima for the wonderful talk and good discussion times in Q&A
Thank you,
sessions.
Yang-Su, and thanks everyone, and thanks for sticking around. I really appreciate it.
Thank you.
Yeah, and do reach out if you have further questions.
That would be awesome. Okay.
Thank you.
Thank you. Thank you, everyone. We have another DDPS seminar tomorrow, so see you tomorrow. Okay. Bye now.
Thank you. Bye.